Yeah, I want to talk to you about Unison, which is a new programming language that we're working on. Um, I am one of the co-founders of Unison Computing, which is a company in America. And our goal is to create Unison, the language, and also create sort of peripheral services around this language. We're currently working on a cloud service that will run Unison programs. And I'm not really going to talk about that today. I want to talk to you about like the language and sort of the fun of playing around with this new language. Okay, I'm also one of the authors of Functional Programming in Scala, which I co-wrote with my friend Paul, who was also my co-founder of Unison Computing. And it just came out for Kotlin as well, Functional Programming in Kotlin. And FP in Scala is now in its second edition, so that's very exciting. Great. So high-level agenda for today. I'm not going to go into a lot of detail. Just going to touch on some topics that each could be its own talk. And so I just want to give you a high-level overview of Unison, invite you to join the Unison community, and just sort of show you a little bit, play around with Unison, just a little. So what is Unison? Unison is a purely functional programming language. It is strongly statically typed. It's very similar to Haskell. It bears some similarities to Smalltalk, but it is radically different from either one of these. It's strictly evaluated similar to Scala or Java or other languages like that, and it's open source. Most of the Unison compiler and runtime are all written in Haskell, and that's all open source on GitHub. So why are we doing this? Why Unison? So we've been programming in high-level languages for about 60 years now, sort of as a species. And we've experimented with various programming language designs, but most languages in use today, I want to say, are not that different from Fortran or Algol, or they actually are Fortran. And but software development itself has evolved, and the languages themselves are sort of falling behind. But there's all this other peripheral stuff that we do as software developers, and very little of it is done using our programming languages. Things like version control and collaboration and builds and continuous integration, deployment, distribution, and then ops, which is keeping the actual program like running somewhere. Like all of this stuff is done with like YAML files and Unix, and not with the actual programming language. And most of this stuff is not intentionally designed by anybody, but it's sort of accidentally and pragmatically created sort of incrementally. It's sort of built upon whatever assumptions came before. We still use old-fashioned text editors to mutate folders full of text files that we then share around with Git and whatever tools that don't really know anything about the structure of code. And then distributed programs talk to one another via ad hoc protocols using towers of technologies that require legions of programmers to maintain. And all of that stuff is like defined out of band by protobufs or something other than the language. So with Unison, we wanted to design from the ground up a developer experience for the 21st century with all of this stuff in mind. And then the overarching non-technical goal is to make programming delightful, or at least not terrible like it is now. But Unison is in its early stages, so it's come a long way just in the past couple of years, but there are a lot of rough edges still. There's a large gap between where the developer experience is and where it could be and where we want it to be. But already it's pretty awesome. I vastly prefer developing in Unison over any other language. at the moment. So the basic impression I want to make on you today is that Unison has the potential to be completely amazing, and that you don't really have to wait for that future to arrive. Like you can join the community and program in Unison today and help make that future happen. And you don't really have to do anything much. You just install Unison and start coding. There's not a lot of setup or like, oh, how am I going to structure my project or whatever. None of that stuff matters. Okay, so what are some big ideas behind Unison? Well, what's this all about? Okay, so the two big ideas behind Unison are that, number one, Unison code is not text. It is structured, immutable data. So the code is a data structure. And number two, Unison definitions are referenced by a hash of their implementation and not by their name, like in most programming languages. So every Unison expression has a unique and deterministic global address, which is a hash of its implementation. All right? So that means that the code is what we call content addressed. So for instance, I have here two functions, have and split, that look very similar. And they each have a hash, but since they have basically the same implementation, modulo the local names, they also have the same hash. And so actually Unison sees these two definitions as not just two implementations of the same function, it sees them as literally the same implementation of this function. So they occupy the same sort of global memory address, which is the hash of the implementation. And the way this works is that when Unison sees a function like this, when you submit this to the compiler, it removes all the local names, removes all the free names and replaces them by hashes of the reference of those names. And what gets actually stored in the Unison code base is something more like this. And then the textual representation of the code is then just sort of like a user interface onto this data structure. So in the end, names don't really matter very much in Unison, or at least they don't have such a prominent function. And you can think of all Unison types and functions, like I say, as occupying a vast read-only store, and every version of everything has a unique and immutable address, which is the hash of the definition. And then the hash can have as many human-readable names as you want, and that makes renaming something, for instance, a trivial non-breaking operation. And then reassigning a name, like changing the meaning of a name, is also a trivial non-breaking change. So in a traditional programming language, you have definitions that are referenced by name, and then if a name gets a new definition, your code breaks, or you break someone else's code. And then if a definition gets a new name, definitely you'll break somebody's code. But in Unison, definitions are referenced by hash and not by name. And then, if you give a name a new definition, the hash remains the same for the old definition, and so nothing breaks. And the same with if you give a definition a new name. So hashes allow us to unambiguously communicate code, across time and space. And a given hash will always refer to a specific, unique Unison object, even across memory boundaries and across network boundaries and disk, and even across revisions or versions. Unison also has no builds, whereas in a traditional programming language, you have this kind of build. And why do we have builds? So the purpose of a build is to ensure that your code can address other code in memory or on disk or whatever. That when some symbol occurs in your code, that it actually refers to the correct thing. And then it type checks and runs all the tests and whatever. But in Unison, all the definitions are referenced by hash in this global internal address space. And so a hash is always the correct version, and you don't ever have to like build to make sure that a name has the correct referent. And then also, a given hash only needs to be type checked once. So once it's type checked and it's in your code base, you don't need to sort of do that again when you rebuild. There's no rebuild. And also, if you've run a test once, we can cache the test result and address it by the hash. And so you can say, well, I've tested this hash, and I don't need to run that test again. We also don't have dependency conflicts. Well, at least we don't have dependency conflicts in the traditional sense. So in Unison, dependencies are as finely grained as possible. So you can depend on just a single function from a library or a single type. And you can depend on two different versions of the same type because they will have different hashes, and so they will, to the compiler, will be different types. And if you try to pass one type off as another, you'll just get an ordinary type error. Whereas in a traditional build or traditional programming language, you'll have build artifacts that are dependencies of your program that are generated by some build, and then they'll be referenced by language version and package name and package version, and then different versions of packages can't really coexist in your build, not without some kind of complicated framework or something. And names can be sort of taken, right? For instance, like in Scala, if you have a dependency on some version of the FS2 library, which is a functional streams library, and then a different library that you depend on has a dependency on a different version of that same library, you'll get a dependency conflict, and you can't compile your code. And adding a dependency is therefore a big deal because transitive dependencies, you bring in all the transitive dependencies, and they invite new opportunities for conflict. Whereas, in Unison, since everything is as finely grained as possible, you can have different versions of different things being referenced by different parts of your code base, and adding dependencies is trivial. Like you can say oh, I just want this one function from this library, and that's fine. You can just add it. Deployment is also different. We do this thing called just-in-time deployment. I don't know how many of you have to develop distributed systems, but I can tell you that my experience is that it's kind of terrible. And the reason why it's not great is that programs generally just describe what a single OS process is doing. And deployment is described out of band by some other tech, like cloud formation templates or whatever. And then the whole build deploy cycle is managed by yet more tech. Whereas in Unison, we have a program that describes an entire distributed system, and then you deploy the program by running it. There's no build step, there's no out-of-band deployment descriptor or whatever. The deployment is written in Unison. Most distributed systems today either use message passing or remote procedure calls or some kind of event bus. But in Unison, you just assume that all the nodes on your network are running Unison, and then the nodes communicate hashes. So you, instead of saying oh, I want to call the function named that, or I want to call a service at this address, you just say, hey, Unison node, run this hash with these arguments, and it will dutifully go and do that. And if it doesn't have the hash, it says, oh, I don't have that hash in my cache, I don't know what this hash means, it can just go and ask you for the definition, and then you can send it over. And it can verify that it's correct by hashing it. Okay, so the other idea was, so that was hashes and names. The other idea was that the code base is not text. The code base is actually an immutable data structure. So it stores your code in a computable form with various kinds of metadata attached, for instance, names, documentation, and tests, and things like that. And the code base knows the type of every expression. It knows the dependency graph of every function, and it knows how your code evolves over time. So it's a database of code that you can query and manipulate. And it's actually literally a SQLite database. And I want to just kind of show you how that works out. So if we can go to you see that? Yeah. So I'm just going to go and install Unison. So if I go to unisonlang.org, if I go to unisonlang.org, you'll see that there's installation instructions for Mac here. And I just go and grab that. And I'm going to go install Unison. That should just take a moment. Yeah, now that's installed. So then if I type UCM here, it'll start up Unison. Great. This is a new code base. I've just installed Unison. So it's now going and downloading the base libraries for me. It's downloading from GitHub, which is where they're stored. But it's literally downloading a SQLite database right now. Okay, and that's done. So it says, welcome to Unison. Maybe we can get this. Yeah, there we go. Okay, so here I'm in my Unison code base, and I get this kind of command prompt, and I can look at what's here. So it's downloaded the base library for me. And I can take a look at what's in there. It's all this kind of stuff in the base library. A list. So this is the base library stored in my code base. And I can ask for like the definition of something. I can say view base.list.++. Oh, it's built in. Oh, that wasn't very interesting. Distinct. Great. So it'll show me the definition of this list.distinct. I can ask for docs, list. It knows all this kind of stuff. I can ask for dependence of say list.empty, dependence. Oh, there's all this stuff that depends on list.empty. So it knows, how things are connected. And it also knows how my code base has evolved over time. So I can actually ask for the history. This is very much like a Git log for base. So there's also you can use the command line interface to browse your code base, but there's also a user interface. So if you type UI in the command line, you'll get a browser interface. So I have it running on port 8081, and I've configured it to be called foo, but the default is something more sensible than that. And so we can see that my code base has base library in here, and I can expand that and look inside, see what's in here. I can focus in on base. It gives me this sort of nice README documentation for base, basic data types, optional values, and collections. And one thing I want to draw your attention to is that this document here is a Unison expression. So the documentation is actually written in Unison. And these examples here are live. So for instance, if I say sort this expression here, then I get the result in here. And this is happening, this is being evaluated live, or it's being fetched from cache, because this expression has a hash. But the actual Unison expression, the document that this is based on, just has like evaluate this inside of it. It doesn't actually have this answer in it. That's evaluated by the renderer of this documentation. So cool. You can open definitions, and all of this stuff is hyperlinked. So set from list. What is that? I can see the definition of that here, and I can get the documentation for set. So cool stuff. This is a nice little sort of browser for this. Okay, so that was the idea that the code base is a database. Why don't we write some, do you want to write some code? Yeah, let's do that. So if I just go in, so if I'm in the same directory, so I started UCM in my home directory, and if in the same directory I create a file that ends with .u, it could be called anything .u, it could even just be called .u, but scratch.u. Open a file with a name like that. I can start coding Unison code in here, or writing Unison code in there, and it will just be picked up when I save this file. So for instance, if I type a definition like twice x equals x times x, and I save, it doesn't know what that is. I need to give it a type twice. It's telling me, okay, I found and type checked this definition in scratch.u. You can add it to your code base. Go to a little scratch space in my code base, and if I add this now in my code base, I can just delete the source, and I can always get it back in here. You notice it looks a little bit different from when I wrote it, and that's because this is sort of a canonical rendering of this. I can always get it back to my scratch file, edit twice, go back in here. Oh yeah, I forgot to save my scratch file after deleting twice. But if you do this edit thing, you'll note that your file gets this sort of line here, and it says anything below this line is ignored by Unison. So it'll put whatever you tried to edit at the top of the file, and below that it'll put this thing which we call a fold, and that's any line that starts with 3 or more dashes. And so anything below here is now a comment. And so you can kind of work in this kind of stack way. So your scratch file becomes this kind of like notebook interface. And so, if I don't care about twice anymore, I can just add a new line with 3 dashes in it, and then I can start doing something else. If you start a line with greater than, and you can type expressions in here and be evaluated when you save. If you start it with test, it'll expect a thing of list of results, so a list of test results. So you can just say check that 1 equals 1. Does that work? Yes. So that was a straightforward test. Okay. So that's sort of basically how you work with this. But I wanna just take you through like writing a little library or a single function or a couple of functions in Unison. It's just like how the workflow kind of flows. So the thing I want to write is similarity on texts. So I want to write similarity with two values of type text. So this is our version of like strings. And it will give us a float, which is between 0 and 1. And I can actually just write that out as a documentation. So this, if I open two curly braces above a definition like this, that is a documentation block. And that's actually defining a new definition called similarity.doc equals that. And the documentation block is a Unison expression. But for shorthand, you can just put it above your definition like this, and that'll just work. So you can then write your documentation in here, and that'll be a Unison definition of type doc. This is a Unison type for the documentation. Does it have documentation? No, it doesn't. Oh, wait. Oh, yes, it does. So I can say returns this is called the similarity index that I want is I want to say that two strings are more similar if they have adjacent character pairs in common, right? And this is called the Jacquard similarity index. The Jacquard similarity index of two text values. So I put this type text in curly braces here, and this is now a link. So this is now a link to the text type inside of my document. So when I go and view this in the UI, it'll actually be a hyperlink to the definition and documentation for text. And we can put hyperlinks in very, just like similar to Markdown. So if I go to Wikipedia over here, I can put the Wikipedia link. I have Wikipedia on my other screen. So you can do cool stuff like that in documentation. Like this will be between 0.0. Now this is these double backticks means that this is a Unison expression in here. And this will actually be type checked. It's not super interesting because it's just a single value, but if I said like 0.0 plus 0.1, it'll render that expression inside of my doc, but it'll also be type checked. And if it had something like this, then this will be a hyperlink to that constant in my document. A question? How does it resolve? Anybody read me that question?
Yeah, sure. So just asking about if two people implement the same function that evaluate to the same hash, which documentation ultimately gets rendered when you publish it?
Oh, well, you can actually have multiple docs for a single definition. It'll just render all of them. Good question. I don't know what order it'll render them. I think that's unspecified. Okay, so it'll be between 0 and 1. So no character pairs in common and one all character pairs. I think it means it's the same string, but there might be some instances where that's not the case. Okay, so I want to write this, and what's a strategy for that? Well, let's see whether we can get the character pairs, like adjacent character pairs in a string. So if I say, find, well, is there anything called like adjacent? In base. That work? No. Pairs. Yeah, that looks promising. List.sliding pairs. Looks 2. Okay, it doesn't have documentation, but it does. 3.list.sliding pairs.doc. Display 3. Great. Put the list of all adjacent character pairs in the list in the order that they appear. That's exactly what I want. So that will give me a list of the sliding pairs, but I don't so much care about the order of the pairs, right? Because I just want to see if they have how many pairs they have in common. So actually, what I actually want is a bag of the pairs rather than a list. So, okay, well, can I find something that turns a list into a bag? Yes, bag from list, great. So I can say similarity of X and Y. I can just say, X bag is bag.from list X. My bag is bag.from list. Oh, wait, sorry, I need adjacent pairs of X and adjacent pairs of Y. And then I want to say what? How many things do these things have in common, right? That's the size of their intersection. Yes? Intersect. Oh, wait, find, intersect. If I put a colon, I'm searching by type. But if I just put, okay, bag.intersect, that's the thing I want. X bag, Y bag, and I want the what do I want? I want the size of that intersection. Size of the intersection divided by the total size, right? Size of bag plus Y bag. Or I guess that is the same. Size of X bag plus size of Y bag. Oh, but this could be 0. So we can say if, let's see, total equals, here. And if, well, greater than 0, else 0. Or is it 1? They're both empty. So which one? They're identical. So, just for writing a simple function like this, you can see a lot of the syntax and a lot of the features of this, and like how you work with the Unison Codebase Manager, UCM, sort of on the side. So typically when I'm working in Unison, I have UCM open in a command line window on the left or on one side, and then my Vim on the other side. And then whenever I save here, gonna go type check. It's like, oh, found a closing else here without a matching then. Oh, it should be then. Okay. Well, one of them is a NAT. NAT is 64-bit unsigned integers, and then float is double precision 64-bit floating point. So these are not the same. So I need to say that this is float, right? I don't want integer division here. I want to float total. I want to float at this thing here too. Okay, not sure what adjacent pairs is. Oh, it wasn't called adjacent pairs. It was called sliding pairs. Okay, it's a text, but I expected a list. Oh, well, find text to the car. Great, to car list. Great, our type checks, and we have documentation. Does it work? That's a good question. Well, we can just go here and start typing. Similarity of foo and foo. No, they should be identical. Oh, I made a mistake, which is that the size, it should be twice the size of the intersection. Right? Because this is size of the, you need to count every element in the intersection twice because it appears twice in the total size. Okay? It's once in each bag. Great, all right. That has now worked. What if we do something like that? Okay, that's half because fully half of the sliding pairs. Only OO is in common. If we say something more, we say carnivorous and a virus. Somewhat similar. So that's, written a little definition here, and I can create a little library in my code base, call that x.similarity or something. And I say add. Now my stuff is in my code base. And I can ask for box, go to the UI. It is now in here. Great. This is a hyperlink to text now. And it's to take me to Wikipedia. Super fun. Was there anything else I wanted to do with this? Should we write a test? Well, yeah, let's write a test. So one thing, can anybody think of a property for this? I'm just going to put this below my fold now, and then I want to write a test. Can anybody think of a property that should hold for this?
Like identity, like something is always the same as itself.
Should return, oh yeah. So for any given string, if you pass it to twice, if you pass it on both sides of similarity, the result should be 1, right?
Yes.
Okay. Just say that, call that. I called it text.similarity. So I have a function called similarity in there too. Let's go back and say move namespace similarity to checkcard. I've renamed that. So I renamed it, and if we had a whole bunch of people with dependencies on this thing, their code would just change whenever they update. Their code, their textual representation of their code would literally change to reflect this name change. automatically. So I want to say similarity dot identity is so I'm going to use a function called runs. There, runs. So runs takes a natural number, a test, and gives me a result. So this type signature is a little bit difficult to read at first, but this is saying it takes a test which is delayed. So it has this sort of backtick, not backtick, but this apostrophe thing here. That means that this whole thing is a computation that should be unevaluated, and it is allowed to have these effects, or is allowed to call on these abilities, abilities. So it can have the ability to generate values, and it can have some other abilities, E. And runs will use the ability to generate values. It'll generate values however many times is specified in this by this nat. And then it'll return the list of results and just pass through this this E ability.
Quick question to make sure I know how to read this. How do I know when I've got an unbound type variable in the case of E versus when I have a bound type variable like gen?
Oh yeah, unbound. So free variables are lowercase. That's really it. And this is actually shorthand for, there's a binder out here between the colon and that, which is for all E, period, and then this follows. But we can omit that because we use this convention. Okay, so the test that we want to call runs, say we want to run that 100 times, and the test should say, now I want to do an unevaluated expression. So I put this apostrophe and I say let. And so now I'm introducing a block which I want to pass unevaluated to runs. So what do I want my test to do? I want it to generate a string. So that is in base.tests. Gen, I think. Next. There it is. So if I say, generate some ASCII text, I think I just say gen.text.ascii. I can say use gen.text ASCII. This is kind of like an import statement. And then I can say X is ASCII. Oh, it's unevaluated, so I need to force it. So I need to say, force that, run this. See that this is delayed here. And that'll have the gen effect, and it'll generate some text. And now I say, well, expect X equals similarity of X and X be equal to 1. Ooh, that's an equality on floats. That's not great. Well, I just say to nat. Oh, that'll round it. What do I want to say? I guess we could just do equality on floats for now. I really want to say it's like less than or equal to 1 and greater than or equal to 1 or something like that. Okay. Or that it's like close enough to, what is that? It's not base.float. do quality equal up to. Is it like an epsilon? ULP.
And forgive me if this is a dumb question, but the reason why we don't want to do equal is because of that weird, like, tiny epsilon that occurs for floating point arithmetic comparisons.
Yeah, like it could be 9.9999999 whatever, and like that's not going to return true for equals. What I really want to say is that the similarity of XX is the ULP diff of similarity of XX and the and 1 should be less than or equal to 1. Something like that. Okay. I want the difference between these two numbers to be very, very small. And so this is the ULP diff is the unit of least precision. Box ULP. Just kind of getting into like the weeds of floats, but.
And might it be presumable for that to like eventually contain a Wikipedia link to like other stuff so you can pull whatever context you need to understand this?
Yeah, definitely do that kind of thing. This doesn't contain that, but it should. So the distance in consecutive 64-bit floating point numbers should be less than or equal to 1. So I want them to be either adjacent or I'll allow a small rounding error here. Run that. Okay, it passed. Can we make it fail? Be less than half? Or 5? No, wait. Yeah. Okay, that failed. Great. So this property holds, and we have a test. We can add to that test. And then if we were in test, it says, well, 1 test passing. If I run it again, it doesn't actually run it again because this is cached. We have a test cache where we cache tests by hash. So we don't actually have to run tests again if we haven't changed either the test or the dependencies of the test. And we can think of another one, like we can test that these change that copy this whole thing.
Sorry, I have a question regarding this property-based testing and equivalence groups. Can you actually output the failed cases so that actually developer can understand what edge cases did fail or not?
Oh yeah, well, so it's not doing that here because like expect this returns a failure, but there's a number of ways that you could see what failed. Like you can, for instance, label your test with the value that you're testing out. Oh, let me see if I can do that here. Can I say expect label text X or something? First argument that expect needs to be a Boolean. Oh, it should be. Does that work? Yeah. So it says pass foo. That's 100 tests. But if I, you can manipulate these labels to say whatever you want. And so, for instance, you can put the value in the label and it'll tell you that. Another thing that people often do is that they will put the actual condition. We can rewrite the test to look like that. where you put the condition here, like this thing here. We put that above. We say that, call that like P or something. And then we want to say expect P. Actually, just expect true. And we can say if not P, then bug X, something like that. Else. If it passed, then that's great. But if I say this, oh, it's the empty string. So, no, it tells me what the value is. Oh, I encountered a bug with the following value. So this is a paradigm that people often use if they want to see the failure. Lots of different ways that you can see the failure, but there's nothing that's like built into the test framework.
And you can pass any given argument to the bug function to actually to format your failure message as you like.
Oh yeah, you can. Bug actually takes anything at all. So you can say like similarity identity failed on X. Like that. Or that's not helpful because it's an empty string. Okay, what I wanted to do was write another test real quick. We say expect the EOP diff any two X and Y actually just the similarity between any X and Y could be between 1 and 0. Oh, yeah, okay. This exposes something about Unison that's kind of quirky. There are no precedence rules in Unison. So this less than or equal to is not special in any way. It's just a function. So Unison doesn't know that like and should have greater should have lower precedence than this. Like it doesn't have any notion of that. So this is actually just saying, this expression is false, and S then should be a Boolean, obviously, and then greater than or equal to is float, and so we have a type error. Actually, need to put parens here. That passed. Great. We can add that. Test. Great. Now we have two passing tests in our little library. And then if I want to like share that with others, I can. So right now it's just a little bit janky. In the very near future, you should be able to go to share.unisonlang.org like that. And here you should be able to share your libraries with others. There is a way you can do that, publish on Unison Share, where you actually have to make a pull request against this GitHub repository in order to put your code on here. And a bunch of people have done that. Like you can take a look at this HTTP client, for instance, by Stu. But it's just a little bit janky at the moment to share your code. But you can push your code to GitHub, or you can like push it to a gist. Let me push it to a gist real quick. So if I say, okay, so I want to push this whole Jacquard thing. Jacquard push.gist. What does it take? Publish the current namespace, just remote. Publishes the content of the current namespace into the repo remote. Okay, so if I just said gh tab, it'll expand that to GitHub. then say, well, mine slash, I have a code base called U2, I think. Unison code base that I made. If I push it there, it'll get pushed to a gist in that code base, in that repo.
So it sounds like it's not very often that you need to leave the UCM terminal to go back to do like any direct Git manipulation or like file system.
No,
manipulation.
there's no Git manipulation. Like you can't actually do that. Ooh, page not found. Why not? Well, it should be gist by github.com, right? Yes. Okay. Yeah, I don't know. I'm doing this wrong somehow. I haven't actually done that recently, but I can also just push to a particular place in my code base. So if I just push using a normal way, and I put a colon, and then I can put a path. So I want to put it into like .text.jacquard under my dot means root, and then .jacquard, .text.jacquard is the path to my where in my code base I want to put this. So I have a bunch of other Unison code in here. And then it'll go and push it to GitHub. The thing is that you cannot manipulate Unison code using GitHub, because GitHub doesn't see the code in any way. So right now we're actually just using GitHub as a dumb store. We're sort of, we're camping out beside a dumpster behind GitHub. Okay, so it doesn't exist there, so it asked me if I want to create that.
Apparently just abusing any Git repository as a blob store, right, for SQLite database files.
That's right. So, no, not usually. Okay, so this is my code base in GitHub, and it's actually just a SQLite database and nothing else in here, which I synced 19 seconds ago. So really the only way to see your code is to either push it to share.unisonweb.org or unison-lang.org, this site, or pull it down into your UCM and browse it there. So we're working on making making it possible for you to push from here into share. So then you'll be able to authenticate with share and just push your code up here. So Unison Share will sort of be our GitHub equivalent, as it were. All right. So, any other questions about this?
So is this SQLite 3 like the de facto serialization format for the binary? So I'm guessing this is pretty much abstract syntax tree with some metadata that you're storing to represent the source code and the syntax tree at the same time, so as well to make them unique globally. So do you actually have chosen SQLite as the de facto format to serialize this data, or is it something which is
No, not at all.
Pluggable?
There's no de facto serialization format. Like we have a number of formats. We have a wire format that Unison nodes can use to talk between themselves. There was a disk, like an on-disk format as well, I think we've deprecated that, but the SQLite thing is, yeah, it stores the abstract syntax tree, in a bunch of tables, and it stores the dependency graph and the types and things like that. But it doesn't actually store the source code. Source code is thrown away because we can always recover it from the syntax tree.
Yeah, cool. Are there any questions here from the room? Marco? No. I thought you prepared a question, maybe.
I could talk a bit more, if anybody's interested. I could talk about the abilities, or I could talk about remote execution very briefly.
Yes, yes,
Well,
that would be a
you
nice
also-
addition.
You mentioned delayed with the apostrophe letter. What it means, delayed execution or delayed expressions.
Oh, yeah, I could talk about more, like a little bit what that means. So, big view. So here, this type. So what this means is really, it's a function that takes no arguments and returns a test and has these effects, or can ask to use these abilities. I can go into abilities a little more, but you can literally just think of it as a function that takes no arguments, and then you call it by passing it no arguments. Either by passing it like the unit value, say, is there a sample? Is test sample? No. Just trying to figure out if I have something I could show. Well, here. So you can do this, like, bang, to force computation like this. Or you can, call it by passing it empty parens, which is a value called unit. It's a function that takes essentially no arguments. And that's
It's just
really just
saying
how that works.
what you mean, passing the code, not the result.
Yeah.
Code.
It's passing a closure,
Yeah. Okay. Get it.
and then you can enter that closure by either passing it unit or doing this, forcing it with bang. And it's actually a synonym for that. Two things are exactly equivalent. There are two different syntaxes for the same thing. And yeah, I can talk about the abilities, and can talk about remote execution. All right, let me just do a little presentation here on the remote stuff. Okay, so here's a function in Unison. It takes a list of natural numbers and returns a natural number. And it does a bunch of things to this list. Like, it will add 1 to every element using this list map function. It'll remove all of the elements that are not divisible by 7, and then it'll sum all the remaining elements. And so now, if you wanted to take this and run it on a very large list that's like living on S3, or on some big store that's like petabytes of data or something, like how do you do that? Well, the sort of traditional answer right now is that, well, obviously you just learn how to use Spark. You read a book that's like 600 pages long, and you use this multi-million line framework to turn your 7 lines of code into, like, that any programmer could write in 10 minutes. You turn that into a distributed program, and so there's this huge increase in complexity. Right, so it's no longer a 7-line program that anybody could write. It's now a huge multi-line framework that requires specialist knowledge, like Hadoop or Spark. And like you could have a job, commanding like several 100,000 euros, like just administering Spark clusters. Like that's a job that somebody can have. And there's practically an entire industry dedicated to just figuring out how to take my 7 lines of code and run them on a large data set in the cloud. Like make them distributed. So what we really want is to write something that's much more similar to this. And in Unison, the way we do this is that we make the code distribute itself. We do this thing called just-in-time deployment. So the distributed version of this looks like that. So we just changed the type, so it's now a seq, which is a distributed sequence of natural numbers. And this remote thing is an ability. And this is saying that this function needs to have the ability to distribute this computation or run some parts of it remotely. And then the rest of the code looks very similar to before, except instead of operating on lists, we're operating on a distributed sequence. And running this function or calling it on a distributed sequence will do all of the migration of the code to the place where the place where a given portion of the sequence is stored. It'll migrate the code to a node that's close to that location and then execute the portion of the computation there. Okay, so very similar to does something very similar to what the Spark cluster would be doing, like a distributed MapReduce, but it does it in 7 lines of code rather than like having to set up and administer a Hadoop cluster or whatever. And we have a whole article that we wrote recently that's actually linked from the Unison homepage called Spark-like Data Structures in Unison. I encourage you to look at that if you want to learn more about this. So this remote thing is an example, and we saw gen earlier. So this is an example of abilities or algebraic effects. But we call them abilities. They're based on a language called Frank, which also calls them abilities. And I just want to give you an example of how those are defined and how they work. So a simple ability that's defined in base is abort. And it's defined like this: ability abort where, and it has a single method or constructor, which is abort. So if you call that, you're signaling to your sort of execution context that you want to abort the program. For instance, taking the head of a list might fail because the list could be empty. So then in the case of the empty list, we call abort. And so head of a list of A's will return an A, and it might abort. Okay? And we can turn an abort into an optional by giving a handler for the abort ability. So that this abort to optional is provided by base, and this is the implementation of it. So it takes an unevaluated thunk or closure that returns a value of type A and might abort. And it puts it in this sort of handle block. So it handles bang P, so force P, and then handle it by pattern matching on the methods or the constructors of the ability. So that's done like this. So here, inside of these curly braces, there will be an arrow, and on the left side of the arrow, will be the constructor with the arguments to the constructor. Abort has no arguments, so it's just no arguments. And on the right side will be a function that you can call to resume the program. Now, since this is the ability to abort, we ignore that function. We don't want to resume. So in the case of abort, we return none. And in the case of some A, then return sum of A. And both of these expressions have type optional A. Okay, so that will turn the sort of effectful closure into a value of type optional A. Another example of an ability is state. Actually, in the base library, this is called store, but it's the ability to have stateful functions. So, for example, so state has two methods. You can put the state. It'll be a value of type S. So if you give put an S, it will return unit. So basically, it returns no value, just the empty value unit. And you can get, which will give you the S. Okay. So this is the ability declaration. And once we have this declaration, we can start using it. For instance, I can have a stack machine, which uses this sort of state ability. And my state will be a list of some values of some type A. And I can implement pop for my stack by saying, well, stack is the stack is whatever is on the state. Like get the state, and then I want to drop a value from the stack and put that into the state, and then return the head of the stack. Right. So I take the head off the stack, put the stack minus the head back in the state, and then return what I got. And then to push a value onto the stack, I take a value of type A, I return unit, but I manipulate the state. And what I do is I cons my value on the front of the stack, which is returned by state.get, and I put that. Okay. One thing to note here is if you're familiar with like monads in Haskell or for comprehensions or whatever in Scala, that there's no monadic plumbing here at all. Like the calling convention for an effectful function is exactly the same as a regular function. So the type system takes care of tracking the fact that this put and get are monadic. So we don't expose that syntactically to the programmer. So you can write in this very direct style that looks a lot like an imperative program. And then just an example here, I can write an adder where I can push I can pop two values of the stack, add them together, and push the result. And you note that this gains the abort ability as well because I'm using head in my pop method. And then I can run my state machine by using a handler. So this actually should be handle with cases rather than matchy with. So this is just wrong. But basically, you pattern match on the methods of the state ability, and so if I have a get, I call my handler on the state. I mean, I pass the state that I have to my handler, and I continue the program by calling this K thing. So this is handlers are written in this sort of continuation passing style. So they can be very powerful. So it's basically like delimited continuations. So you can have crazy stuff like there's a debugger ability that Paul wrote that allows you to like step through your program and like go backwards and stuff. So you can write very powerful control constructs using this stuff. And then an example of running this where I have a little stack program where I push 4 and 3, and then I say add, and I get 7. So another example of this is the remote ability. So I go back to my function here that's manipulating a distributed sequence. It uses this remote ability. And the remote ability, like the ability declaration for it is like pretty complicated, but it's basically based around these 2 primitives, which are called fork at and await. And we have this notion of location, which is like an abstract place where the execution of Unison programs is possible. So fork at takes a location and a delayed computation that returns on T, and it returns one of these sort of tasks. And then you can await a task to get the value that it computed. So this thing here can this is this thing here. The second argument here is a closure that can have some effect G, it can throw exceptions, and it can do remote stuff. And G can be all kinds of like location-specific things. You'll know that location takes this G type argument. So whatever this ability G is can be location-specific. So for instance, some locations might have the ability to run stuff on a GPU, or they might have the ability to like talk to a quantum computer or something. And then you'll be able to make requests to those handlers at the remote location. So it could be basically anything you want. And then the implementation of fork at will take the unevaluated Unison expression here, this closure. It'll send the code to the given location and ask that location to execute it. And then we'll wait for it to complete. So yeah, that's all I have to say about abilities. Are there questions about that?
No questions here? I
Alrighty.
don't think so, Rúnar. Cool.
So yeah, just sort of in closing, where we are right now, so this is as of February last month, we just added like a faster runtime. We have this visual codebase browser in Unison Share. We just revamped the codebase format, which is now a SQLite database. And we have this computable documentation format. We have a distributed programming API. We have standalone bytecode files, so you can actually compile your code to like a bytecode, and then you don't have to wait for like UCM to start up to run your program. Roadmap for the next few months is that we're going to continue to build out Unison Share. We're going to have pull requests and code diffs, and so like code reviews. You're going to have Unison native hosting, so basically you'll be able to just push your code to Unison Share to share it with others. We want to, keep developing the base libraries, and I also want to invite you to write libraries for Unison. It's like it's a pretty green field at the moment, and like you could have a huge impact on the Unison community. And we are pretty soon going to pilot this Unison Cloud service, which will allow you to execute your Unison programs using the remote ability on our cloud. And we're also working on native compilation, which will, that means like really fast Unison programs that don't have to go through the Unison interpreter or Unison runtime. And we're also hosting our first Unison conference sometime in the June timeframe, and so you should look for an announcement about that soon. So, yeah, I just want to invite you to start coding in Unison. Just install it, download the binary, and open your text editor and get going.